Hello, everyone. In this video, we're going to discuss 4.1 exponential functions. And the objectives that we're going to cover are identify key characteristics of exponential functions. We're also going to graph exponential functions, find the equation of an exponential function given a graph, and then use transformations to graph exponential functions, and finally use compound interest formulas. You probably have a general idea of what exponential functions are and what they look like from your previous math course. But let's first start by comparing linear functions with exponential functions. When you had studied linear functions changed at a constant rate. The slope changed the same rate every unit. But for exponential functions, the growth is a little different. So if we compare the exponential function, this exponential function, f of x equals 2 dx, and this linear function, g of x equals 2x. This linear function, if you look at how it changes for the x value 0, 1, 2, 3, 4, 5, the 0 to 2 and 2 to 4, you can see that it grows at a constant rate. And it looks like the change is 2 every unit. Now with exponential functions, if we look at it, it does change, and it is also increasing. But how is it increasing? Well, from 1 to 2, we had to increase by 1. From 2 to 4, looks like a change of 2. 4 to 8 looks like a change of 4. 8 to 16 is a change of 8. And then from 16 to 32, change of 16. If you look at this, it seems to be growing, but it grows at a bigger rate each time. Another way to think about exponential growth is by multiplying the growth. So from 1 to 2, we would have multiplied by 2. From 2 to 4, the same. 4 to 8, the same times 2. And it looks like it multiplies by 2 each time. So another way to think about linear functions is it grows at an additive rate. You would add the same amount each time. Exponential functions, we multiply by the same rate each time. Okay, let's graph this function by looking at a table for the same function 2 to the x for the values -3 to 3 for this x values. For -3, if you evaluate that, we get 2 to the -3rd, which is 1 over 8. We evaluate 2 to the -2nd, we get 1 over 4. 2 to the -1st, we get 1/2. Or 2 to the 0 is just 1. 2 to the 1st power is just 2, and then 4, and then 8. So we use those points to plot the points on this coordinate plane. -3, we got 1/8. And then -2 is 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4, and then 3, 8. We have this exponential function. You see it's growing and increasing as we go from left to right. So let's look at some key characteristics of this function, f of x equals 2 to the x. Okay, the domain, let's see how far it goes towards a negative x values. It keeps going, so negative infinity. It's the graph also goes to the right. So the domain is negative infinity to infinity. The range, the lowest y value is 0, but it never reaches 0. So we're going to put a parentheses, and the highest y value, because it keeps going up, we have 0 to infinity. The graph as x approaches infinity, so that means as we go to the right, the y value, f of x, approaches also infinity. As x approaches negative infinity, so as we go left, the y value, f of x, actually approaches 0. F of x is always increasing. When we say that, we mean always increasing from left to right. And this graph will never touch the x-axis. Therefore, we say there is a horizontal asymptote at the x-axis, and the equation of this horizontal asymptote is y equals 0. Okay, the y-intercept is at 1. If we wanted to write it as a coordinate point, that would be 0, 1. Okay. Let's look at what exponential functions are in general. So for any real number x, an exponential function is a function of the form f of x equals a, with b as a base raised to an exponent x. And to just generalize the properties of exponential functions, which we looked at for a specific case to the x above, for all functions, f of x equals a to the b to the x power, where a, your a value, is greater than 0 or positive. This a value is a non-zero number, and this is the initial value of your exponential function. B, your base, is any positive real number, and it can't equal 1, because otherwise it wouldn't be an exponential function. If B is greater than 1, then we say f of x is increasing, right? It's going up from left to right at an increasing rate. If your B value is greater than 0 or less than 1, so say a fraction between 0 and 1, like 1/2, then f of x is decreasing at an increasing rate. So it gets smaller, and it gets smaller at an increasing rate each time. Okay, the domain of f of x is all real numbers, and if we write that as an interval notation, we would write -infinity to infinity. And the range for f of x is all positive numbers, and as an interval, that's 0 to infinity. If your a value, your initial value, is a negative number, then the range is all negative numbers, or -infinity to 0. The y-intercept is your initial value, or a. As a coordinate, we would write 0, a. There is no x-intercept if your exponential function is in this form. That is not to say exponential functions never has an x-intercept, and we'll look at some cases and when we talk about transformations where exponential functions does cross the x-axis. The horizontal asymptote of an exponential function in this form a to the b to the x, is y equals 0. Okay, in the next video, we'll talk about how to graph exponential functions.